Welcome to SanfordFlipMath. This is PreCalculus. We are working through the Conic Sections, and as we do that, this is just a very short little video that kind of shows you why they're called Conic Sections, and as the cross sections of a cone are illustrated by slicing through this cone or double cone, as it were. Let me show that one more time. It's only 9 seconds. Circle, ellipse, parabola, and then that works into a hyperbola. We'll see hyperbolas in the next video, not this one, but the one after this. And so we're continuing our work on the conic sections. We've already talked at length about circles and parabolas. This is the screen shot of most of what happened in parabolas. Remember that? And the screenshot for circles. And both of these have a definition like the set of all points in a plane equidistant to a fixed point, and then the one before that, the set of all points in a plane again just means a flat surface, equidistant to a fixed point called the focus and a fixed line called the directrix. Well, ellipses are the same thing, same kind of thing, and the idea here is this time it's the set of all points in a plane such that the sum of the distances to two fixed points, is constant. So for instance, I could have a fixed point here and a fixed point here, and both of those are called foci or focuses. Okay, and so I have two of them bad boys. And the idea here is that if I'm going to sketch in where the ellipse would be. And the idea is if I pick a point on the ellipse and if I measure to the distance to the first focus and measure the distance to the second focus, if I add those together, no matter where I am on this ellipse, I get the same answer. Okay, so I could be right here. So the distance to the first focus, distance to the second focus. If I'm not saying those distances are the same, this D1 and this D1 are not the same, but the idea is that if I add those together, I get the same answer. So red D1 plus red D2 is equal to the blue D1 plus blue D2, or if I looked at adding those two up, same idea. So again, D1 and D2. So no matter where I am when I add those two focus distances, that sum is constant. Okay. This is a picture of what some people do like on a bulletin board. It's a little tricky, but again, that idea that here's that D1, here's D2, and that pen point or pencil point is on the ellipse. And if you do that carefully, then that string maintains that constant distance as you go all the way around. Okay, so that's the idea there. Okay, all right. So with that in mind, just a quick little note here. So here's that picture again. There is a bunch of stuff that where this actually plays out. Orbits in space are typically elliptical orbits, and whatever they're orbiting around is at a focus, and there's always the second focus, but there usually isn't a physical being there or a physical entity there. It's just, that's just part of being an ellipse. But it's one of Kepler's laws in astronomy that orbital motion is elliptical typically, and just about all space motion is. So and there is another weird thing. I used to attend church at what used to be Brightmoor Tabernacle. That building's now Christian Tabernacle. Christian Tab, I think it's called. And in their lobby, they actually have an elliptical ceiling. Okay, so here's the ceiling of the room and of the lobby area. And if you stand about here and you have your friend stand about here, if you talk, the sound actually bounces in such a way that it goes to the other focus. So the reflective properties are from one focus to another, and this is a place to not gossip. Just so you're aware. Okay, all right. With the ellipses, there is a lot of vocabulary and a lot of stuff going on. Okay, so here you see the ellipse definition again, and just a quick little highlight here. This is actually going to be important, and let me give you another version of that. And I know it feels weird to write it in either of those ways because you're so used to seeing a squared plus b squared equals c squared. Okay, so the typical form for the equation of ellipse looks like this. Okay, looks kind of like a circle, only instead of having r squared over here, this is always 1. Same over here, and I'll show you the distinction between those two, and I would recommend just focusing on one of them. And the idea is underneath the x squared and underneath the y squared are two different numbers that are a squared and b squared. And those numbers act kind of like the radius. It's just you have, the thing that makes an ellipse different is the radius is not the same all the way around. You have like a different radius, and I shouldn't use that word radius because it's really not a circle, and that's a word really for circles. But you'll see kind of what happens here. So let me just give you a quick example. Okay, so I'm going to make one up here on the fly. Okay, over 9 equals 1. Okay, and you'll see these numbers like 4 and 9 a lot because they're easy to work with. Okay, so this is an ellipse, and we'll see the ellipse equations in different forms, but this is a fairly typical way to write the ellipse equation. Again, the thing on the right side is always 1. Okay, and then this guy is actually b squared right here, and this is a squared. And the reason it's that way is because for an ellipse, the a squared is always the bigger one. And the reason is because of that equation that we just saw, that c squared equals a squared minus b squared, or if you prefer, a squared equals b squared plus c squared. And this c is going to be important. That's the distance. Probably should call it little f, but I didn't, and the books don't. The distance from the center to a focus. Okay, and we'll see that in a minute, but the reason that a squared is always bigger is because of that. Okay, and I want to do a little sketch of this. We'll sketch the graph, and so let me write down some stuff first. Center is at 1, -2. Again, inside inverse, just like with circles, just like with parabolas, etc. And then, so as we said, a happens to be 3 since a squared is 9. B is 2 since b squared is 4. That's pretty much all you need in order to graph it, and it's very much like graphing a circle. So I'm going to go to 1, -2. Okay, and then since b squared is 4 and b is 2, and since that's all in the under x, that's the horizontal distance. So horizontally from the center, we're going to count 1, 2, and put a point. And then 1, 2, and put a point. I'm going to do the same kind of thing. Well, with this, a squared is 9, so a is 3, and that's under y, so that's up and down. So we're going to go 1, 2, 3, and we're going to go 1, 2, 3, and then sketch it. Okay, now, yeah, that looks more like an egg, I guess, but the idea is it's supposed to look like a circle. It's kind of stretched. Okay, so some extra terminology. So it's really not hard. Some extra terminology here. There is something in here called a major axis. There's something called a minor axis, and this was, I don't have any reason why I'm switching between capital and lowercase. This is listed here in this little spot also. Okay, so the major axis is 2a. So in this case, 2 times 3, 6. The minor axis is 2b, and so 2 times 2 is 4. Okay, and so what the major axis is actually this length. It's kind of like a diameter. Okay, and major implies bigger. Okay, so here's minor. And it's probably worth noting that sometimes people talk about a semi-minor axis, well, or the length of the semi-minor axis, and so that would be 2. And then some people talk about, again, similarly, the semi-major axis. And you guessed it, that would be 3. And so semi just means half. Okay, so that's semi-major axis. Here's the semi-minor axis. Okay, and really there's only, well, there are 2 more things to talk about. Sometimes you're asked to find the vertices. Okay, which you know already is the plural for vertex. Well, for an ellipse, there are 4 of them. And what they are is the endpoints of the axes. Axes, not I-S-E-S. Okay, so the vertices for this thing, well, you'd start at the center and we went up 3, so this would be like at 1, 1. And then at 1, well, we started out at -2, went down 3, so that'd be -5. This going to the left, okay, so this would be -1, -2, and something else, -2. So this is 1, 2, 3. Okay, and so really all you do is start at the center, and those are those points when you counted left and right 2 and up and down 3 from these numbers. Okay, okay, so vertices. Then the last little bit is foci. Okay, so focuses. Okay, so foci, as I mentioned a minute ago, come from this relationship a squared equals b squared plus c squared, which is a rearrangement of the Pythagorean theorem. And I could go through a big long thing, but basically the short version is the foci have to be on the major axis. And what ends up happening is there's a little, this little guy is C. This would be A, and this would be A, and it has to do with the way the distances add going around the ellipse from the definition, and this would be the B. Okay, so again, foci are always on the major axis, always inside the curve, always on the major axis, the longer part. Okay, and then they follow this rule because of the way the right triangles work in there. And if you want, I can sit down and talk about why it works this way and not c squared equals. It has to do with the labeling. And I just don't want to spend forever on the video. Okay, so we already know that a squared was 9, 3 squared. B squared was 4 plus c squared. So if I subtract 4 from both sides, then c ends up being plus or minus the square root of 5. Now, remember that the center of this particular ellipse was at 1, -2. And remember, long ways, the major axis is vertical. So that means this gets added or subtracted up and down, so to the y value. Okay, so that means the foci will be at 1, -2 plus the square root of 5, and at 1, -2 minus the square root of 5. So that's a 5. Okay, and yes, you can combine that and write plus or minus if you want. So those are the foci. That's it. Now we got a couple of other issues to deal with, and one of those is you know that the equation is not always going to start off in that form. So let's do an example where it's not already starting out cute. Okay, so we could have something like this, and let me spend just a second talking about why this has to be an ellipse. Okay, please note that x squared and y squared are both present, so it cannot be a parabola. A parabola would be if it was just about x squared or just about y squared. Okay, also note that the coefficients are different. If this would have been just x squared plus just y squared, not 9x squared, not 16y squared. If it would have been just x squared, just y squared, circle. Or even if it would have been 9x squared and 9y squared, it still would have been a circle because you could divide out the 9. Okay, so this is an ellipse. The other critical thing is that the sine and the sine are the same. Okay, so if they're both positive and different coefficients, ellipse. If one's negative, it'll be a hyperbola, and we'll deal with that in the next section. Okay, the next little chunk here. Okay, all right, so let's get on with it. We need to make it look like this. Okay, and don't sweat whether it's x first or y first. That's not an issue. I always write it with the x's first, just remembering that a squared is the bigger one. This original sheet had a squared as the bigger one, but what they do is they switch the x's and the y's all the time. So I don't do that. This starts out pretty much like a circle progression. We're going to have to complete the square twice. The catch is that we're going to have to do a little bit of factoring first. Okay, so let's get the x's together and the y's together. And I would leave space, but I know I'm going to have another step in here anyway, so I'm really not worried about it yet. And I'll go ahead and put that 47 on the other side by adding it to both sides. Okay, so I'm going to do a little. Remember, just like with the parabolas, if there's a number in front of the x squared, it has to be factored out. Okay, and this is where I'm going to leave some space. Okay, so process is really just like what we did with circles and with parabolas at this point. So I got to do half of 6 is 3, 3 squared is 9. Now, I'm really not just adding 9 though, because there's a number being multiplied out here. So I'm really I have to add 81 to both sides. So I added really 9 times 9. Okay, and then on the other side, same idea. Half of 2 is 1. 1 squared is 1. So it's that whole half of b squared. And then I have to add 16 to the other side to balance this out. Okay, all right. So I'm going to go ahead and do a little bit of factoring here. So this is now x plus 3 squared, okay, plus 16 and y minus 1 squared. And I guess I need a total for the right side. Okay, and that total is 144. Okay, now, it looks a lot like a circle equation, and you might even be tempted to say the radius has to be 12, since that looks like r squared. But remember that in the standard form for an ellipse, we have equals 1 now. So what that means is I'm going to divide both sides by whatever this number is so that I can make that into 1. Okay, don't subtract 143. That makes a bigger mess. So on the right side, it's just equals to 1. On the left side, I need to do a little bit of reducing. Well, 9 happens to go into 144. And what is that? 16 times, I believe. So this becomes, and then I think they kind of flip-flop here. So 16 goes into 144, I believe, 9 times. Okay, so now we can start answering some questions. This is standard form. Okay, so that's a big deal. That's like the biggest part of doing this. And then after this, it's a bunch of questions to answer. Okay. Okay, so that's standard form, did that. Okay. Center then. Well, the center, again, this is inside inverse kind of thing. So -3, 1. The length of the major axis. Well, the semi-major axis, well, let's start out with this. A squared is 16, so the semi-major axis is 4. And so the whole major axis would be 2 times 4, or in other words, 8. Okay. The minor axis, again, the major is the bigger one. Minor axis, semi-minor is 3, so the minor axis, 2 times 3, 9. Okay, so we have to do the foci and we have to graph. Now, let me do, I would like to do the graph first. Okay, and we'll work from the information we already have here. Okay, so center is at -3, +1. Okay, and then we're going to go left and right 4. okay, because that's under the x. Okay, so there's the right fourth. So we have a vertex at 1, 1. We have a vertex that looks like -7, 1. Okay, I'm not going to write those down, but that's what they are. We're going to go up 3 because that's under the y, and we're going to go down 3. Okay, okay, and I know my ellipses probably look just as great as my circles did. Okay, and if I was on a grid, it'd look a little better. Okay, now so we've done the graph. Yep, that one. Okay, and now we need to do foci. Now, just a quick little reminder here. The major axis is horizontal this time. Foci are on the major axis, somewhere to the left and right of the center in this case, okay, because it's longer horizontally. So a squared equals b squared plus c squared. Again, this c is the distance from the center to the focus. Okay, and the ellipse has 2 of them. Okay, so this is going to be 16 equals 9 plus c squared. And I know, I'm sorry, it's 16 and 9, and this is going to be real common. So that's not too bad, I guess. So 7 equals c squared. So c equals the square root of 7. And it's real common to just leave it like that. Okay, so plan on leaving it like that. So it's moving left and right. Now the center, if you recall, was at -3, 1. So that means the foci will move from the center. They're moving left and right. And that's it. Now, I know that feels a little weird seeing the square root in there. It doesn't feel very concrete. So let me just do a little bit of typage, and then we can actually kind of locate where those are on the graph so you can get a better feel for it. Okay, so if I do -3 plus the square root of 7, I get -0.354. And then the other focus would be at -5.646 and 1. Okay, so those foci are actually located at, there's somewhere around here, -0.354, and let's see, this is -345, so somewhere over here. Okay, so that just gives you a better feel. All right, well, I haven't done one backwards, and I really need to do one backwards, but I'm not going to do it here. We'll just have to do it in class. This is already plenty long. So, all right, well, thank you for hanging with me, and welcome to the world of ellipses. We have one more conic section after this to go, and thanks for hanging with SanfordFlipMath. Bye-bye.